All right, let's go ahead and get started. All right, so I know you guys want to know what's on the midterm exam, but I haven't written it yet, so I don't know. I don't know what exactly will be on the exam. I have some ideas for problems, and I guess I can share those ideas with you so you can at least start preparing. But I haven't written the questions yet, so I can only give you kind of some vague ideas of what I'm thinking here. Let me see, something's wrong with my... And then I was preparing my lecture notes or lecture slides for today, and the typesetting took so long, I didn't finish everything. but well, anyway, okay. So I'll just kind of write like my midterm ideas. Okay, so one problem will be like with matrix notation. And I'll probably ask you to find the gradient of some function, with respect to a vector, okay, in kind of matrix notation. I'm still figuring out what exactly, the function will be in matrix form, some function that, returns a scalar value, okay? With respect to a vector in matrix notation. So, like examples are like the loss function. This is not going to be, will be like the OLS loss, which looks like t minus x w transpose t minus. I realized we haven't done anything in like handwriting, so I don't know how you guys have been taking notes, but vectors get little arrows over them, and then matrices have serifs. Okay, so to kind of denote some matrix X, you kind of put these serifs on them, and that's how we'll do it, okay? And then, I would ask you to find the gradient of this with respect to some function, okay? Obviously not this, something different, but this is kind of the idea that I'm going for, okay? And then I guess find the gradient, and then also, if applicable, solve for where the gradient equals 0, right? And then, if you did it for this, you would get w hat is equal to X transpose X inverse X transpose T, right? Okay, so that's one idea I have for a problem. Still figuring out exactly what to put in there. Midterm 1 guidelines. Okay. All right, another problem I'm thinking of. Again, I'm still writing the exam and I haven't figured out everything. Number 2, I was thinking of a numeric gradient problem. And so this will have, I provide some kind of function. That takes in a vector and outputs a scalar. And then I'll tell you to kind of numerically estimate the gradients numerically. Using some epsilon equal to like 0.001 or something, Maybe I'll artificially inflate it to like 0.01. Okay. All right, and so if you've got some function of say w, then your gradient can be approximated numerically by doing f of w plus epsilon. No, it doesn't work this way. Sorry, getting ahead of myself. Eraser. Okay, so the gradient will look like this. Whatever, okay, however many terms are in W, and it can be approximated by doing f of W1 plus epsilon with everything else intact minus f of the W divided by epsilon, so on and so forth for the rest of the thing. So you just, anyway, telling you too much, but numeric gradient estimation, I'm thinking of that. So obviously you'll need a calculator. Bring a calculator. Other problems I'm thinking of. A gradient descent problem. What's that?
A lot of gradients.
A lot of gradient stuff. It's
Leave one out.
Yeah, I would like to do something like that, but okay, hang on. All right, is this okay? Can I move to the next whatever? All right. Okay. So another idea, and again, I'll write some things out, and then I might decide to change my mind or something. If I change my mind drastically, I'll let you know. Okay. gradient descent, okay? Again, I give some kind of function and some arbitrary starting point. All right, I provide a gamma, and then and you perform, you know, maybe 2 iterations manually. Gradient descent. Manually, so this is, I don't know, I think I've made you do manual stuff of like coordinate descent or whatever kind of algorithm you have. Same kind of idea here. I don't know what else I can say about this problem. And then another idea I have for a problem is like a cross-validation thing, except everything I can think of for cross-validation is like very computationally expensive for a human. So I'm trying to think of like how to do this in a low, like, I don't want it to just be like button mashing on your calculator. Like all of these things involve button mashing on your calculator. So I was thinking of doing a leave one out, cross-validation. And I think it would probably have to be a very small data set. Either 3 or 4 data points only. And kind of two coordinates in 2 dimensions. And then if I do this, I would probably have to provide a lot of stuff. Like even asking you, like if we had 4 data points and we did leave one out and you have like 3 data points, even then, like trying to find the least squares regression line for a set of 3 data points is a non-trivial matter for a human. And so if I did this, I would probably have to provide like all 4 fitted lines. So like, and then I don't know, like, I'm thinking about this, okay? So like, if you have points A, B, C, and D, then I would provide kind of, you know, fitted line 1, which will be fit on BCD, fitted line 2, fit on ACD, etc., 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 to fitted line 4. And then I guess you would have to find the cross-validation error. I think that's reasonable, but I'll have to see what it looks like when I write out a problem like this. So this is an idea. Again, I don't know if this will be it's hard to know, right? And then I have to write the test for 45 minutes. So have to kind of judge how long these things should take. And then the last idea that I have, so these are all ideas. Again, I haven't finished writing the exam, so I'm not sure what's going to turn into a real problem, okay? But I guess these are, you know, all worth mentioning so you study. The last one will be kind of regularization. And I guess I would just ask you to kind of, again, small data set. Probably 3 or 4 points. And then I would ask you to compare. Now, so for a given set of parameter estimates, calculate OLS loss, lasso loss, and ridge loss. Okay, so it'd just be kind of a comparison of these things for maybe a given set of parameter estimates. And, maybe I should write given sets of parameter estimates, and I would have to, again, judge how computationally expensive this is for a human to carry out and things. I don't know. Maybe I'll just change my mind and ask you conceptual questions on like the effects of ridge versus lasso. I guess I'll put that as an option as well. All right, so final option, maybe just conceptual questions. You know, like effect of lambda on ridge or lasso loss. Maybe effect of gamma on gradient descent. I don't know. Other stuff. Okay, so I'm all kind of wrestling with some of these things. A lot of these are kind of little, you know, computationally based. I mean, it is a computational class. I just, you know, so as I write, I'm also keeping in mind that it's a 45-minute session, right? I mean, class time is 50 minutes, and I like to have time for passing things out and collecting them. So I try to write it for 45 minutes in mind, keeping also in mind, you know, how to do all of these things. And I always run through the exam myself and time how long it takes me, and I try to judge it accordingly. And of course, I give you a huge buffer because I know exactly what I'm doing and things. So, okay, is that all right? At least giving you an idea of what to expect. All right, so we'll, I guess we'll leave off with that. And we'll take a look at today's stuff. And I have to finish the notes because I ran out of time. With the LaTeX. All right, so here we are. All right. Week 3, Friday. Good Friday, okay. Oh, yes, we'll start off with a quick review quiz. So, if this is our neural network, this is kind of where we started off. what are the dimensions of x, the dimensions of w1, w2, and y, okay? So you can talk to your neighbor if you want. The dimensions of these kind of these matrices going into the network. And I guess maybe it's not clear. X is going to be n by something, okay? Like leave a generic n in there because you've got n observations. So.
Yeah.
All right. So what do we say? X is going to be n by 2. Okay. W1 is 2 by 3 because we've got 2 going in and 3 going out. W2 is 3 by 1, 3 coming in and 1 going out, and then y is n by 1, okay? So that's what we're going to get, okay? So we go n by 2, 2 by 3, 3 by 1, and the result when you do all of that multiplication is going to be n by 1. Okay, so here's our thing labeled out. So W being 2 by 3, we've got 6 things, W1, 6 things in W1. W2 being 3 by 1, we've got 3 values in there. And then we've labeled our hidden layer Z, Z2, I guess. And then, and so when we multiply X by W, we get our Z's. We pass that through our activation function. Element-wise, it comes out as A's. And then we multiply the A's by the W's, and we get another thing of Z's, and we pass that through our activation function, we get our Y hats, okay? So here's our W1 and our W2 matrices. And right now we're using the sigmoid activation function, which is, you know, again, has fallen out of favor, but it is differentiable everywhere, and it, you know, squishes our values to between 0 and 1, okay? And so just kind of reviewing all of these things, we do X times W to get Z. So that's, you know, X times our weight matrix W, that becomes the values going Z. We pass Z through our activation function F, okay? Which does not change our dimensions, okay? So Z is n by 3, A remains n by 3. We multiply A by the second weight matrix, which is 3 by 1, so that becomes n by 1, that's going to be Z3, and we pass that through our activation function F, and we get Y hat, which is going to be n by 1. And so our fitted values, if we kind of just chain everything together, it looks like this, f of x times W times W2, and we have that, okay. And so our loss function, we've got some kind of loss function. And so here I've got kind of like the mean squared error. And I'm going to try to follow along with the video, the Welch Labs video, and he calls it J. And what he's done is he's multiplied our loss function by a constant, basically 2n, okay? Or I'm sorry. It should be n over 2. Okay, I'll fix that. N over 2, and so we get, you know, 1/2 times this, and that just kind of makes things a little bit cleaner because, you know, when we take the derivative of this, the 2 comes down and it cancels out, so we don't have to deal with the 2 or anything. And then, you know, because we're just multiplying by a positive constant, the value that minimizes this function, that minimizes j, is going to be the same value that minimizes L. So we're just going to be looking at this function j, which is pretty much our loss function, just multiplied by constant, and then we'll take the gradient with respect to that, okay? All right, so now we're going to start talking back propagation. We'll see how far we get, and maybe it's okay that I didn't finish all of my typesetting because maybe we won't even get to the end. We'll see. Okay, so back propagation, this is like, I don't know, sometimes the scariest part of dealing with neural networks. There's a few approaches to this. One is you can draw a computational graph. Here I'm going to just kind of stick with just calculus, but conceptually they are the same. Okay, so this whole idea behind backpropagation, starts with just like, how do we train this network, right? So we've got this thing. We have a total of 9 coefficients or 9 weights that we need to estimate. These are the parameter values that we need to estimate to train our network, okay? And so training the network just means finding these weights so that when we plug in x, the thing that comes out on the other side, y, looks a lot like our data. We want good predictions between x. We want our network to take in our x and make good predictions of y, okay? And we've got 9 values to play around with, and so we've got this, and we're trying to minimize the loss there, right? So we train weights by trying to minimize the loss function, and to minimize the loss function, we're going to use gradient descent, okay? Because trying to solve for finding the gradient of this is one thing, but then solving for where the gradient is equal to 0 is not really feasible, okay? So finding where the gradient is equal to 0 here is quite challenging because we have these activation functions with these sigmoid activation functions, and they're kind of nested in each other, and so we'll see it's a challenge just to find the gradient in of itself, but we'll manage, we'll get the gradient, okay? But then figuring out where that gradient is equal to 0 is quite tough, so we use gradient descent, okay? We say we're gonna start, so imagine we're in 9-dimensional hyperspace, I guess, okay? So with gradient descent, the illustration was, in 2-dimensional space, or where you've got a loss function, it's kind of in 3-dimensional space, and you find which way is downhill, and you just take a step downhill, right? The gradient points uphill, and you say, well, if that way is uphill, then downhill has to be in the other way, and you just take a step downhill, and then once you take a step, you find the gradient again, and you say, that way is still uphill, so I'm going to go in the other direction and move downhill, okay? We've got 9 parameters to mess around with now, so I guess we're in, 10-dimensional hyperspace, and, with respect to the loss function, we say, okay, that way is uphill, that's where the gradient points to. The gradient says this, I don't know, this 10-dimensional vector points uphill, or 9-dimensional vector points uphill, we're going to take a step in the opposite direction, and we move downhill, okay? Whatever downhill means in high-dimensional space. And we just repeat that, and if we keep walking downhill, then we should get close to the bottom of the valley, okay? Now, gradient descent has all sorts of issues where we get stuck in local minimums. It's pretty bad about that. And so people suggest often starting at different starting locations, and that helps. Another issue is that you might end up in a region that is not at the minimum, but it's like really, really, really flat, okay? Like almost totally flat, but not quite, but not exactly flat. And so, so the gradient will still point as far as what uphill is, but the magnitude of the gradient is going to be quite small because you're on this, just like it's like having a pool table that's just a tiny bit off, not level, and so maybe the ball will roll just a tiny bit, but it will roll slowly until I guess it picks up momentum or something, and so that's another issue that we have to watch out for. But anyway. The idea is, in order to do gradient descent, which is what we're going to do, we got to find the gradient, okay? And so finding the gradient just means figuring out the derivative of kind of our y-hats with respect to our W matrices, okay? And so, so we want to eventually get these two gradient matrices, okay? We've got the gradient with respect to W1 and the gradient with respect to W2. And if we had bias terms, we would also have to figure out the gradient with respect to bias matrix 1 and bias matrix 2. Okay? So that's, and I put future homework exercise, okay, for that. So in class, we'll kind of go through these two things, and then I'll leave it up to you to do these in your future homework. Okay, so we're going to start off here. Okay, so again, all the way back here, we've got this function j to be 1/2, and it's going to be kind of the sum of the difference between the y_n's and the yn hats. Okay, so here we are, and so the gradient of a sum is the sum, or sorry, the derivative of the sum is going to be the sum of the derivatives. So this is where we are, and so if you take the derivative of y minus y hat squared, it's going to be you bring the square down, and that cancels out the 1/2, and you have y minus y hat. But then now we have to apply chain rule, okay? And so we would apply the chain rule to the y hat part, which is we've got -1, and we've got the partial with y hat and with respect to W2. Okay, there's no, I don't have to worry about the gradient with respect to yn itself, because yn is a fixed value. It's something in our data, so it is not going to change with respect to this weight matrix W2. Okay, so we really only have to figure out the gradient with respect of y hat with respect to W2, because we know that the data, the fixed points of yn, will not change with respect to W2. Okay, and so I'll just move the negative sign over here, and right now we're just kind of focusing on one individual data point, y sub n, right now. Okay, and so the whole thing is going to be a sum of all of these things. And so if we ask, well, what is the gradient of y hat n with respect to our weight matrix, that can further be broken down, because if we look at what y hat is, it is the result of passing z sub n through our activation function f. Okay, so we're going to have the gradient of this is the gradient of y hat with respect to z sub n, and then we have the or not the gradient, the derivative of z sub n with respect to W2. So we've got the derivative of y hat sub n with respect to z sub n, at the third layer, and we've got z sub n with respect to W2, okay? So we're still at kind of this node. We've got the y hat coming out, and then before that, we've got kind of z sub n3 going in, okay? So here, we say y hat is equal to f, the sigmoid activation function applied to this, okay? So we can just say the derivative of y hat with respect to Zn is just f prime of the function, okay? And that's effectively what I'm going to do. I'm going to just replace this with f prime, okay? But probably we need to figure out what f prime is, and so here's f. F is 1 over 1 plus e to the negative t, so what is the derivative of that? Okay, f prime. All right, is that okay? So, so here, just remembering quotient rule from your whatever Math 31a, you got if f is u over v, then you got u prime v minus uv prime over v squared. And so we'll let u be 1 and v be 1 plus e to the negative t, and then you've got u prime, which is 0, minus u times v prime. So v prime is negative e to the negative t over v squared, and so this is what we get, okay? So f prime of t is this, and so if I plug in f prime of zn at the third layer, it's just going to be exactly that, okay? But just to kind of keep things tidy, I'm going to just leave this as f prime zn3, knowing that it represents this, okay? So we left off here, and we've got the gradient of j with respect to W2 is this, okay? We've got negative of the difference between our actual value and the fitted value, and f prime of zn3, and then we have to have, and we've got d, the derivative of zn3 with respect to our weight matrix W2, okay? All right, and so this is where things start to get a tiny bit messy, okay? And so, so if we recall, the matrix Z3 has dimensions n by 1, okay? And it's the result of taking our matrix A, which is n by 3, and multiplying it by our weight matrix W, which is 3 by 1. Okay? And so if we focus on just one value, okay, Z sub n, which is a scalar value, 1 by 1, that's going to be the nth row of our A matrix multiplied by our weight matrix W, okay? So this is going to be 1 by 3 multiplied by 3 by 1, okay? So this is what we have. And so here, if I ask what's the derivative of this with respect to W2, okay, so I've got a scalar value, and I say what's the derivative of that with respect to this, okay, then the derivative needs to be 3 by 1, okay? And so, I don't know if you guys remember, what's the derivative of some vector multiplied by another vector here? That's going to be the transpose of that vector, okay? So here I get the derivative of this with respect to W2 is going to be A sub n, the nth row of our A matrix, our A2 matrix, transpose, which will be 3 by 1, okay? So this is, you know, for one value, it's going to be the nth row of the A matrix transpose, and we get 3 by 1 here. Is that all right? Okay, so I'm going to go ahead and I'm going to throw that in here, okay? And so, so this is where we left off, and so this part is all just a 1 by 1 scalar value, right? So yn, the actual value is, you know, for one data point, this is one value, the fitted value is one value, and then the activation value of Zn, that's also one value, okay? But over here, we have, you know, a 3 by 1 matrix, okay? And so if I wanted to try to get rid of this summation sign and say, well, what's this whole thing with, and so so over here, this is fine. You can do a scalar multiplied by a matrix, and you're just going to take that scalar and kind of recycle or broadcast across the matrix. And so that's not an issue, okay? But if I wanted to get rid of this summation and use the actual matrices themselves, then we run into some issues, okay? because y is an n by 1 matrix, okay? So y minus y hat is going to be n by 1, and then z is an n by 1 matrix, and A, for the whole thing, the whole A matrix is 3 by n, okay? And so we have all sorts of dimensionary issues here, okay? So, but we also know, so this is this is where kind of vector calculus starts feeling a little bit funny, is, you know, we have to think of like, okay, well, what's happening here? We've got a scalar multiplied by a scalar here, multiplied by a matrix, okay? But these are the elements that we want to multiply together. So we kind of need to, you know, rearrange things and figure out exactly how this multiplication needs to be done, okay? So because we've got a scalar times a scalar here, what we're going to do is we're going to line up this n by 1 matrix and this n by 1 matrix, and we're going to do element-wise multiplication. So I've got basically a column n by 1 and another column n by 1, and I'm going to just multiply them element-wise, okay? And so for that, so here I've got the n by 1 and the n by 1. I use this symbol to represent element-wise multiplication. I don't know if I was trying to look online like what the exact symbol is, and there's not like a lot of people use this, but this is not consistent in every textbook, okay? And then I can just rearrange this to be brought into the front, okay? And so this will line up. So this n by 1 element-wise by this n by 1 is going to form just n by 1 column, okay? And then if I rearrange, just bring the A transpose, the A matrix transpose, and bring it to the front, I've got, you know, a 3 by n here, and I can multiply it against this, okay? And so in the Welch Labs video, he calls this whole thing, this negative y minus y hat, element-wise multiplied by f prime of z3, he calls that delta 3. And so this is what we have, and we get this. We get our A matrix transpose times delta 3. So A is 3 by n. I mean, A is n by 3, but transposed it's 3 by n, and multiplied by n by 1. And so this will result in a 3 by 1 matrix, which is exactly what we want, okay? And if we think about what's happening here, this is basically, because we've got each of these, we've got n values going on here, and then we're kind of adding them up. This is going to kind of be, you know, a weighted sum of all of these elements in n. Okay, so each of our n observations will contribute towards what the gradient is with respect to W2. Okay, so so the video goes over this, you know, fairly quickly, but I don't know if you guys have watched this, but you know, rewatch the Welch Labs video on back propagation, and he talks about kind of each observation having like a little vote in deciding what the gradient should be. Okay, so you know, for one observation, it might say like, okay, you know, to improve our loss function, we need to move in this direction, and then another observation might say to improve the loss function, we need to move in another direction. And so the resulting thing is, you know, each of these things kind of point in a different direction, and they kind of just add up and form you know, a direction. You're just adding all of these different vectors together, and adding them together gives you just kind of one overall direction. And so so we end up there. The video, you know, I think the videos are great, but they play in the video, my critique is he just he just says let's ignore the sum, and then let's come back to the and then let's just throw in the sum a little bit towards the end, which is fine, but it feels a little bit hand wavy. And so I tried to preserve keeping the sum and all of these dimensions intact, so that I hope the math steps here make sense. Okay. So it looks like we're going to run out of time. The next thing we need to do is we need to find the gradient with respect to the first weight matrix, and so I guess we'll pick up on that on Monday, and then I'll finish off my notes.
I can't meet for a one.